the applications that we proved last time, namely the Similarity-Trotter point line incidence theorem and the Spencer Similarity-Trotter unit distance estimate, which were, of course, applications of the crossing number lemma. Those two results can also be applied to generate more results, and so I want to show you kind of how math tends to build on itself, and things improve over time. So let's start by reminding ourselves. So Spencer, Similarity, and Trotter showed that in any large finite set of n points in the plane, no distance can occur more than, and we're going to say, it's got to be bounded above by n to the 4/3 times. So if I've got n points, then I can't have any distance occurring more than n to the 4/3 times, up to multiplicative constants. So I want to do a quick application of this fact, and I want to apply it to the distinct distances problem. So theorem: in any large finite set of n points in the plane, there must be at least n to the 2/3 distinct distances. Now, I think this was first proved by Moser using slightly different methods, but this proof is rather quick, and it's a nice little application of Spencer Similarity-Trotter and pigeonholing. So, quick proof. Let the pairs of points, how many pairs of points do we have? N choose 2, which is roughly n squared, pairs of points, be pigeons, and let the distinct distances be holes. Let's suppose there are t distinct distances. Okay, I guess this doesn't have to be parenthetical. This could just be another sentence. Okay, suppose there are t distinct distances. Well, by the pigeonhole principle, there must be a hole with at least, number of pigeons divided by number of holes, pigeons in it, with at least n squared divided by t pigeons. Right? So I guess we'd put a ceiling here if we're going to be really careful. All right, so that's just the pigeonhole principle. We've got n squared pairs of points. Each pair of points determines determines a distance, right? So if I give you a pair of points, it only determines one distance. There are t distinct distances given by this point set, and so each pair of points goes into one of those holes, one of those classifications. So by pigeonhole principle, there must be a hole with number of pigeons divided by number of holes, pigeons. There must be a distance with at least this many point pairs. But we also know that no distance can occur more than n to the 4/3 times. So we take this as our upper bound and this is our lower bound, and we get that n squared over t is bounded above by n to the 4/3. All right, so I'm saying that there must be a distance that occurs at least n squared over t times, but we know that no distance can occur more than n to the 4/3 times. So if I do the algebra here, I'm going to get that t is bounded below by n to the 2/3, as claimed. All right, so this was just simple pigeonholing applied to the distinct distances problem using this estimate on the number of unit distances. Now the distinct distance problem has been essentially solved in the plane using much more sophisticated methods, but this is just a step between, the first example, the first theorem we proved was n to the 1/2, so now this is n to the 2/3. The conjecture is just a little bit less than n. And if you'd like to know more about that, email me, let me know. So this was one application. Now I want to do another application. And I should say, I mentioned that I had recently written a paper that involved recurrence equations. And basically, if we take this, just as a side note here, if we take this problem, how often can a single distance occur? And we start looking at, well, how often can a pair of distances occur between a triple of points, or how often can, say, 4 distances occur measured between 5 points? What we get is some sort of a self-improving estimate. So the estimate on k distances says something about the estimate on k plus 1 distances, and that the set of techniques that we put together led to a recurrence equation, which we then had to solve to put in that paper. And I had hoped to present that for you in class, but I think what I'll do instead is just, I definitely don't want to go through it here in this little YouTube lecture. But if we can, if you have questions about that, you can email me, and if we have time during the Zoom lecture, then I'll pull that paper up and show you the relevant parts. Okay, so this was the Spencer-Semerity Trotter. Now let's go back and do Semerity-Trotter, which was, again, roughly the same type of proof, based on the crossing number lemma. But Semerity-Trotter was in any large finite set of endpoints and m lines in the plane, the number of incidences, the number of point line incidences, is bounded above by, let's say, is I, which is bounded above by nm to the power 2/3 plus n plus m. So I want to give you an application of this theorem. There are many. In particular, if in the previous question we were looking at how often a unit distance occurs, we can actually measure how often a particular dot product occurs, because dot products are constant on lines, whereas distances are constant on circles. And we get a whole bunch of estimates using this. But what I want to do is something kind of different. I want to talk about additive number theory. So let's suppose that A is a subset of the real numbers. It doesn't have to be, but just for today, let's talk about real numbers. And the size of A is n, which is finite. And we're typically going to be dealing with large finite sets. I will define the sum set to be A plus A, which is the set, let's just do this as A plus B, such that A and B are elements of A. And I can similarly define the product set, AA, to be the set AB, such that A and B are elements of A. So the sum set is the set of sums, just pairwise sums of elements of A, and the product set is the pair of products. Now you can actually do this as, the sum of two different sets, so the product of two different sets. There's a whole bunch of stuff we can do here, but for today's application, we're just going to be dealing with A times itself and A plus itself. Now there's a conjecture due to Erdős. Of course it's due to Erdős, that given any set of size n, then the max of the sizes of AA and A plus A should be bigger than n to the 2 minus epsilon for any epsilon positive. That is to say, it should be roughly n squared, either products or n squared sums. Not quite, we're losing an epsilon here, but what's the idea? Well, let's suppose a is the numbers 1 to 100. If I compute the sum set of the numbers 1 to 100, those are going to line up a lot, and I'm just going to get natural numbers between 2 and 200, right? Well, I'm going from 100 to about 200, so that's like a constant multiple. But if I look at the set of products between 1 and 100, I would have a whole bunch more products. So the size of the product set would grow faster. It would grow almost like n squared-ish. So while we don't yet have this conjecture satisfied, I want to show you one of the early results due to Elekesh. So again, we're looking at, given a set of real numbers, we want to show that either the sum set is big or the product set is big. And this is called the sums and products problem. And again, this general area is called additive combinatorics. Or combinatorial number theory. There are a whole bunch of related problems that are very interesting. I think I pointed out the book by Town Vu. It's a really nice book. There are a pair of books by Mel Nathanson, and Mel normally has a conference in New York at the end of every May, and that's one of the highlights of my year is going to the CUNY Grad Center and getting to see all my friends that we meet the same time every year. But with coronavirus, we're not going to physically meet this year, so we might do some sort of Zoom conference. But anyway, and that conference is called, of course, Combinatorial and Additive Number Theory, or CANT. Super fun conference. So let's prove just a really basic result by Elekesh on this combinatorial and additive number theory stuff. And we're gonna prove the following theorem, that given set A, given a set A, it's a subset of the reals such that the size of A equals n, large and finite. Then we have that the max of AA and A plus A is bounded below by n to the 5/4. This is a beautiful, beautiful result. So let me prove it to you. And this one is not as simple as just pigeonholing. Like the last one was pretty straightforward pigeonholing. This one's going to require a little bit more work. And I want to tell you roughly what I think about this result, or how I think of this result. Then I want to present it and then sort of remind you of my perspective. So the first time that you read this paper, the original paper due to Elekesh is like, Elekesh is E-L-E-K-E-S. Elekesh. You read this paper, it's like 3 pages, and first page is half of it's white space for the title, then half of it's like introduction, history. The third page is basically just a few lines of references. So the whole meat of the paper is really like 1 page, and it's laid out so crystal clear. I mean you can just read it. Unlike a lot of math papers where you have to read a line, write it down, think about it, do some side calculations, figure out what all they've left out. You just read it and you're like, wow, yeah, that's good math. Beautiful argument. What I think he does is he wants to generate a way to map sums to products. And he wants to relate sums and products in this way. And that shouldn't be a surprise because this is a result on the sums and products problem. So what we're going to do is, given our set, we're going to construct a point set. And I'm going to call it script P. And this point set will be defined as the set of sums and the set of products. It's going to be defined as, let's say, AI plus AJ, comma, AK times AL, such that AI, AJ, AK, and AL are elements of our original set A. So this is going to be the point set. It's not quite a. It's got a lot of structure, but it's not quite a structure that I can really name. So it's going to be a set of. I mean, I guess it's a Cartesian product set, right? But it's a set of sums paired with products. So there's a lot of structure here. Then we're going to construct a set of lines, and I'm going to call it script L. And the set of lines is going to be the graphs, pardon me, the graphs of these linear equations, which are y equals, and I'm going to write a sub s times x minus a sub t, such that as and at are elements of A. So this is going to range through this whole family of lines. And these lines are, if you look, remember I said I wanted to kind of map sums to products. If we look at this as, x is an input, y is an output, it's going to take any number x as an input, and the number y that it outputs will depend on x, so for each of these lines. And in particular, as it ranges through the different choices of AS and AT, if x happens to be an element of the sum set, if it happens to be of the form A plus AT, so some element in A plus AT, then when I subtract off AT, I'll have an element A here. Right? And then if I multiply AS by A, that's going to be an element of the product set. So what this set of lines does is, among other things, it takes elements of the sum set as inputs and spits out elements of the product set. Now there's a whole bunch of other stuff that could happen here, but in particular, that's going to be in this structure. So again, we're thinking of mapping sums to products. Okay, so let's count things. Well, the size of P is going to be the size of the sum set times the size of the product set. Okay, it's going to be the size of A plus A times the size of AA. And that's because, among other things, we can think of this as a Cartesian product set, right? For every element in the sum set, I'm considering every element of the product set. So, size of the Cartesian product is the product of the sizes. Okay, fine. How many lines do we have? Well, for each choice of AS and each choice of AT, we have a line. How many lines? Well, so then the size of L is going to be exactly the size of A quantity squared, because I choose an AS and then I choose an AT. Now we notice these should all be distinct because the elements of A are distinct. We can determine lines uniquely by their non-degenerate lines uniquely by their slope and intercept, and we're going to I think this is fine here. Okay, so these are the points, these are the lines, and now, of course, we're going to apply the Senger-Trotter theorem. So how many incidences will there be? Well, we're going to bound incidences above and below. Well, first off, we notice that each line is incident to at least n points. And why is it incident to at least n points? Well, for every input of x, which is of the form AT plus an element of A, I'm going to get an element of y that is, I'm going to get elements x and y that are on my point set, right? So if I have an element from my point set that is of the form, let's say AI plus AT, then x minus AT will give me AI here, and I'll have AS times AI. So if I have an element of the sum set go in here, which is something plus AT, then I'll have an element of the product set come out. And it'll be something from A times AS. Now there could be, I don't know, maybe there will be some other incidences. I'm not saying anything about that, but I know that there will be at least the size of A incidences for each line. So the size of A times the size of L, which is the size of A cubed. We'll have at least that many incidences. Now, I'm bounding this above by, well, number of points times the number of lines to the 2/3. So size of P times the size of L to the power 2/3. All right, that's the number of points times the number of lines, plus the number of points, that's the size of P, plus the number of lines. Okay, and that's just applying Senger-Trotter. So I have values for all of these, so let's plug them in, right? Well, I've got A cubed bounded above by, and again, we're losing potentially a multiplicative constant here. Bounded above by, well, P is, I've got A plus A times A to the 2/3 plus, and again, P is A plus A times A plus, and L is again A squared. Well, I can ignore A squared because I know A cubed is not going to be less than A squared. So that term goes away. I don't really have to worry about that, right? We see how that works? So now the only thing I have to do to prove this theorem is I have to reconcile this left-hand side with this right-hand side. Well, what would it mean if this term dominated? Well, if this term dominates, right? If this term dominates, then that means that the max of these, which I'll just write as max for short. So when I write max, I mean this maximum here. This max has got to be bigger than, whichever is the maximum of these two has got to be bigger than A to the 3/2. All right, and that's just pigeonholing, right? If I've got the product of two things bigger than A cubed, size of A cubed, that means the bigger of the two of them had to be bigger than the size of A cubed square root, right? Okay, and 3/2 is definitely bigger than 5/4. So if this dominates, we're very happy. So this is, again, kind of a degenerate case. We don't have to worry about that, because if this dominates, then we're done. So what that means is this is probably going to be our dominating case. Oh, and I, you know what I did? I said it's the size of P times the size of L. I wrote the size of P, and I did not add in the size of L. Let me fix this. So this is the size of P, and then the size of L is, of course, A squared. All of that to the 2/3. Running out of space. So now the main part of the argument is going to be what happens when this is the dominating term. That is to say, if I have A cubed bounded above by this. So let's check. Well, I'm going to assume that this is the part of the inequality that matters the most. Let's just tilt down here a little bit. Let me raise both sides to the 3rd power. So now I've got A cubed is going to be A to the 9th, is bounded above by, well, this was all this raised to the 2/3, so now this is going to be A plus A times A times A times A squared, and all of this squared, and it was raised to the 2/3, but not, remember I've cubed both sides. So now let's take the square root of both sides, and I've got the size of A to the 9/2 is bounded above by size of A plus A times the size of AA times A squared. So this squared was inside the parentheses. All right, let's keep going. Now I'll divide both sides by A squared, so I'm going to subtract 4/2, and that is A now to the 5/2 is bounded below by A plus A times AA. right? I've divided both sides by a squared, so I subtracted 4 halves from the exponent. All right, now again, the max of these two is going to have to be bigger than the square root of this, and the square root of this is a to the 5/4. So that tells us that the max of these two is going to be bigger than the size of a to the 5/4, and that's what we've claimed. So again, the big idea here, so from here on down, it's just arithmetic, okay? The meat of this proof is we use Senger-Trotter right here, okay? So what did we do? We started with some set of real numbers that was large and finite, and we claim that the max of either the size of the product set or the size of the sum set is at least n to the 5/4. And how do we do that? Well, we made a set of points in the plane which consisted of sums and products of elements in our set A. Then we constructed a set of lines which mapped the sums to the products. So this kept track of some sort of correspondence between sums and products. Once we were able to get traction on this correspondence, we were able to use the Senger-Trotter point line incidence theorem to sort of tension, right? And how do we do this? Well, we set this up to where these lines would have many intersections. So, they would have a cubed incidences, at least. But we know that the set that sets of points and lines in general can have no more than this many intersections, right? That's the Senger-Trotter point line incidence theorem. So we apply that, and we plug in the various values, and of course we remember to throw in the size of L. We don't leave that off like I did a few minutes ago. And we notice that, the number of lines is the size of a squared, and that's not going to dominate size of a cubed. So that term goes away. The number of points is the size of the sum set times the size of the product set. And if, in some, really nice setting, that was to be the dominant term on this right-hand side, then we would already be doing better than we thought, right? And so what we said was, well, this is probably, the hard case. So let's assume this term dominates. And we have to do a little bit of arithmetic if this term dominates. But, if this is bigger than a cubed, we still win. Oh, and just a word on, why, I've got this plus this plus this. Why am I just picking one at a time? Well, this is an asymptotic estimate. So I'm going to assume that one of them is bigger than than the other two. And if not, well, then I just throw in a multiplicative constant, right? So suppose in some strange set, this term was the same size as this term for some reason. Well, then I can bound this term as, just twice this term will give me a bound for this plus that, right? So I can really just pluck these off one at a time as long as I'm ignoring multiplicative constants. If all three of these happen to be the same size, then by estimating just one of them, then I lose a multiplicative constant of 3. Again, it's a constant multiple. I don't care. But yeah, this is just a beautiful argument due to Elkesh. Again, we're mapping sums and products together, and this is really, I think, just a beautiful piece of mathematics, and shows the power of understanding things and applying them in different settings. So anyways, thanks so much for taking my course, and I guess I'll be talking to you soon.